Estimating noise parameters. Easy. Now, given that you have an image that suffers some sort of noise interference, you get a portion of this image, let's say a small section of it, and then build a histogram, an image histogram of that. And with the histogram, you get the shape. This is obviously a Gaussian noise. You get the shape, the standard deviation, and the mean values. And now you have your noise model. You can build exactly the noise model and use it in your filter to get to reconstruct the image, to get a better image from your noisy one. This one is the Rayleigh noise. So you do the same thing. Get a histogram, get a small portion of it, a small portion of the image. Get a histogram. This is a Rayleigh noise. This is a uniform noise. And that's the process in a nutshell. You get the distribution of pixel values for one. It has to be a uniform region. Like you cannot get this this portion of the image across distinct regions, right? Because then you might have 3 peaks, and depending on the quality and the quantity of noise, your 3 peaks. So for you're going to have one Gaussian for this, another Gaussian for that, and another Gaussian for that. And depending on the quantity of noise, you might have some very complex shaped distribution here in your histogram, and you can't do anything with that. But if you manage to get a homogeneous portion of your image, such as the one that I've taken for the example, here, or here, or here, you are capable of getting a good estimation of the mean and variance of your distribution. Now, once you get the region, try to fit all the distributions with the parameters obtained. You got the mean and variance, try to fit Gaussian, a Rayleigh, and so on and so forth, and get that with the smallest error. What does it mean, picking up the one with the smallest error? Imagine that you have this Rayleigh noise. You picked up this, you are in this case, and you try to fit a Gaussian. Now try to predict the intensity levels for every point here. You see that these points have no reference to the actual distribution. So these are error points. Instead, if you try to fit a Rayleigh distribution, which will be something like this, you get fewer errors, right? So you pick up the distribution with the smallest error. Easy peasy. Selecting a strip where you're going to cut the image. How do you select these kind of regions to do your statistics on the image? If you select one that's too small, you won't get enough statistics. If you get one that's too large, you risk picking 2 distinct regions. Right? So there's always a human heuristics into it. It's always the image processing expert who's going to select the best regions. And if you want to get a very good reconstruction, you have to get estimates from every region in the image. So you should get one estimate here, one estimate there, one estimate there, right? Because there is no way of knowing if the noise distribution is homogeneous throughout the image. You may have a distinct noise distribution here that's totally different from that, and of course you may not. You may have a distribution that's distinct from this, but Okay, you can make your method as complex as you wish. So depending on, again, your applications. If your application is industrial inspecting of non-delicate material, that's fine. If your application is medical image processing for robot surgery, then you really have to be careful about getting very good statistics of your image to get noise filtering. Now, if you know the type of noise that you're dealing with, if you know the type of noise that your image suffers from, you select the appropriate filters. Gaussian or uniform, you can use the average filter, the mean filter, or non-local means that we've seen in the previous lectures. Salt and pepper, medium filter is great, right? And so on and so forth. The book has a good description of the type of noise and the filter that you should use. And with that knowledge, you can design your error measurement according to the type of correction used. Now, as you're going to be studying, if you haven't already, it's not enough to just get a picture and then an image with some noise and say, oh, look, I filtered it. But you want to know how well your filter worked. Now, how do you do that? So, if you know the type of noise, or you have an estimate of the type of noise, say exponential. If you get your estimated function and subtract it from the original function, you should have an exponential as output, right? If you get your estimated function, which the correction, minus the noisy image, you should get the type of noise that you have. If you don't, or depending on the difference, you can actually measure how different your curve is from the exponential, and that is a measurement of how well your algorithm worked. So there's quite a few other filters. You don't need to know them all by heart, but you need to be aware of their existence. Considering noise only, which it's the process of denoising, we're gonna see other kinds of degradation soon enough. In remembering the process that we are doing, right? We're walking on a neighborhood in applying some sort of operation here. We've seen two such operations, right? We've seen only one mean filter, the arithmetic, where you get from your neighborhood, you take out, you get the mean values of the pixels around and substitute the middle pixel by the mean value, by the arithmetic mean. But you could also apply the geometric mean that has this form here. Right, where each restored pixel is given by the product of all pixels in the subimage. Subimage is the window that you are passing, is the moving window, raised by the power of 1 divided by mn. Right? We have other mean filters, harmonic filters, which you apply this formula. You apply this formula where? You apply this formula on your window and substitute the middle pixel by the result of this equation. Contraharmonic, it's very good. It depends. Contraharmonic has an index here that if the index is less than 0, it eliminates salt noise. If the index is greater than 0, it eliminates pepper noise, but not both at the same time. Again, which filter you're gonna use, that depends on the kind of noise that you have. This is an example of an X-ray image of a circuit board. This is the image corrupted by Gaussian noise. And this is the result of the image filtered by filtered with arithmetic mean filter of a size 3 by 3. And this is the result of a geometric filter, of applying the geometric mean filter to this image. Which one is best? They're pretty much the same, right? But if you look closely, especially on regions around here, for instance, where it's pretty much noise, you see that this portion here is smoother, and it's smoother in regions with great where basically there is only noise in the image without losing the definition of edges where you need them to be, right? So this is an image corrupted by salt and pepper noise. And this is the effect of applying a contraharmonic filter with Q 1.5, and this is the result of that's image. Hang on, let me see. Right, again, so this is an image corrupted with salt and pepper noise, and this is an image corrupted by salt noise only with the same probability. And this is image C, is the result of filtering A with a contraharmonic filter of Q equal to 1.5, and this is the result of filtering B, this image, with a contraharmonic filter with key minus 1.5. So you see that the harmonic filter, the contraharmonic filter with 1.5, did a very good job on the pepper noise, and the other one, the contraharmonic filter with a negative coefficient, did a good job on the salt noise. By selecting the wrong sign of contraharmonic filtering, with results, instead of getting this very nice effect, we actually add more noise. So this is the result of filtering this image A, filtering A with a contraharmonic filter of minus 1.5, and this is the result of filtering an image corrupted with salt only noise, which is this one, with a contraharmonic filtering with coefficients 1.5. Okay, and that's all for this section. The next section we're going to see a few other filters that are based on order statistics. I'll see you there.